Though now you know that you can deal with individual compounds and how to find the oxidation states of unknown elements, but what you mostly deal with are redox reactions in examinations. By redox reactions, I actually tend to mean the redox equations, and you are supposed to deal with complete equations in exams. So we'll start with a very basic one. In your chapter, the equation that has been repeated the most is the reaction for metal displacement. You might have seen magnesium in solid form reacting with copper oxide in solid form. And since it was a displacement reaction, magnesium was more reactive than copper. So magnesium was capable of displacing copper in a reaction like this, forming magnesium oxide solid and copper solid, right? Now, the most common question is to give you an equation like this and ask you which compound or which element exactly undergoes oxidation, which one undergoes reduction, or which one is the oxidizing agent, in other words, or which one is the reducing agent. Now, you have seen equations solved in the book in which they have used arrows, like the book told you that this one is oxidation, going through the process of oxidation. This one is going through the process of reduction. But how would you know? So our recent practice is actually going to help us with that. What we need to do is to calculate the oxidation states for every single element present in there. Let me erase this. We'll redo this again. Let's start with the rules that we had learned in the previous class. And let's apply those rules. Do you remember that any element that is single, uncombined, has a zero oxidation state as per the
Yeah,
rules?
yeah.
So definitely magnesium is zero over here and copper is zero over here. You have seen oxygen to be -2 most of the time. So probably this oxygen is 2 minus, as well as this oxygen is 2 minus. Since magnesium belongs to group 2, magnesium belongs to group 2, so
That's
that
true.
makes magnesium with +2 over here. Since here it is in a compound form, it's in a combined form. Copper
Mhm.
is a transition element. We don't know about copper. So we need to put it as X. If I put it as X, then X plus -2 is equal to 0. This proves X is equal to +2, right? If I move 2 over there, this would have a state. So what I'm going to do is that I'm going to quickly erase it, rewrite it as +2. Now, let me tell you that uh, in terms of tips, what we do tell our students is that if, mathematically speaking, if any element moves from a smaller number to a bigger number, notice magnesium is going from 0 to +2, and copper is doing the opposite of moving from +2 to 0. So
Yeah.
definitely reduction and oxidation are actually happening on magnesium and copper. Nothing's happening to oxygen because oxygen stays from -2 to -2 from on left and right of our equation. So if I notice magnesium is going from 0 to +2, notice smaller mathematical number to a bigger mathematical number, this is oxidation, all right? And copper is going from +2 all the way to 0, which means from a bigger mathematical number to a smaller mathematical number, which is actually the exact opposite. So it would definitely be, bear with me,
But sir, oxidation is loss of electrons, right?
Yes, oxidation is loss of electrons, which means that the change in this case would be oxidation, and this one is reduction. Make sense?
No, sir, because magnesium went from 0 to +2, so it has gained electrons, right?
No, beta. Remember, if you gain
Oh,
electrons, your charge becomes negative. Your charge
yeah, yeah,
becomes positive and you lose electrons. That's the confusing point for students. We're
yeah,
using the
yeah,
word lose, but we are using a bigger number. So that's the contradictory part. That's because of the charges. That's how two negative behave. Make
yeah,
sense?
yeah,
Okay. Now, you clearly know that the one undergoing oxidation is a reducing agent, and the one undergoing reduction is an oxidizing agent. So this means in this case, magnesium or the entire magnesium oxide, you can either tell them that the magnesium is the reducing agent, and copper or the entire copper oxide, either one can be considered as an oxidizing agent. You can either take out the only element, you can talk about the whole compound. Both ways, it's considered correct. That's what you're supposed to do for equation. And remember, you won't have to deal with single compound. You'll have to deal with multiple compounds present in a single equation. You'll have to deal with an entire equation. That's what Edexcel questions look like.
yeah.
Okay, let's do another question, another similar question, but this time I'm just going to write the equation and I am going to leave the rest for you, which means you need to identify the oxidation part of the reaction and then the reduction part of the reaction and then the reducing and the oxidizing agents respectively so that you can completely answer the question on all four grounds, which commonly are Edexcel's practice of asking questions. Okay, a similar reaction can be carried out between aluminum in the form of solid foils. It can react with iron, actually to be precise, iron trioxide, and it literally produces aluminum oxide and it produces pure iron, and the whole reaction is carried out in solid states for every material. Okay, so which one's oxidizing, which one's reducing? I'm turning the annotations on. It's entirely up to you whether you'd like to do it on my screen or you'd like to do it on a piece of paper and send me the picture. Take your time. I can wait. When I see the answers to oxidation, reduction, reducing agent, oxidizing agent is all correct. But the error I find in all of this is that on your left-hand side, the oxidation state for iron has not been correctly calculated. Now, let me do it here for you. Okay, the point being that this being 0 minus 2,
Sir,
yeah,
one sec. I think I know my mistake. One sec. Let me just try once again.
yeah, sure, go ahead. So if you understand this, let's try another equation. Now, whenever hydrogen gas is passed through on the surface of copper oxide, the black solid we have previously used in the equation of top this page, it usually gives us the red-brown copper in solid form, plus we get vapors on the surface of the utensil we're forming. Just a second. So let's rewrite the equation. Hydrogen gas plus copper oxide solid, giving us copper solid plus water vapors. So what about this one?
All right. Mhm.
For water, hydrogen is plus one. Plus one should be inside the bracket and two outside, since the number of atoms are two and the state of hydrogen is plus one. This would also eradicate the mistake you have made at the bottom. And oxygen, of course, would be minus two. So hydrogen is actually moving from zero to plus one, not to two. Copper, on the other hand, is going from plus two to zero. So your answers for oxidation and reduction are basically correct. You haven't mentioned oxidizing and reducing agent, but I assume since you now understand it, it won't be difficult to point that out for you, right?
Yeah.
Okay, good, good. Just make sure you change it. Hydrogen would be from 0 to plus 1. So move plus 1 inside the brackets and take the 2 out of the brackets.
All right.
Okay, that
Yeah.
will actually correct the mistakes. Okay, so I'm going to stop sharing over here. Just a minute. I'm going to open the same document we have discussed before, the types of reaction document. And when you go to the last pages of these documents, let me actually enlarge it for you. Now, when you go to the last pages of this document, you'll find many equations to solve, starting from the very simpler equations such as the reaction of hydrogen and oxygen forming water, all the way to more difficult equations, and not just the oxidation equations or the simpler reduction equations, formation reactions. There would be even displacement reactions in there. So it would be easier for you to practice more equations. All right. So
Yeah.
if you want to practice more equations, you can take equations out of these pages. Just simply write the equations on a clean piece of paper and then solve them on your own. Okay.
Uh-huh.
You can
Yeah.
take any of the reduction equations out of the same chapter of the book. If I don't go with this, if I go with this one, just a minute. If I go with this one, actually, this is Reactivity Series 145.
Also, sir, sometimes the transition metals, I guess, they usually give the charge of that, right? Like iron
Yes,
1, iron 2.
yes. If the names are present, yes, they tend to give the charge with it. That
Sir,
actually helps the student with the reaction.
what
Yeah,
if
go
there
ahead.
is no charge given?
Then we find it out.
Like we use from a periodic table?
Yes, we actually find it out with the X system that I've given you.
Mhm.
Okay.
Yeah.
Either we do that, or there is one more way that we can do it with. Now, this way is pretty easy for ionic compounds, which means metal and non-metal. For example, it's Al2O3, then we do understand that this 3 was taken over here or 2 was taken over here by a cross multiplication method. So this
Mm.
3 would go over here in the form of plus 3. This 2 should go over here in the form of minus 2. That's what the states are. So reverse cross multiplication is another method that helps us with it. But this method will not work if we ended up with a simplifying step. For example, for copper oxide, this method does not work. Since it was Cu2O2 and we simplified it as CuO, so of course you won't find any states to cross multiply it with, reverse cross multiply it with. So this doesn't work for the compounds that we have applied the simplification step, but if we haven't applied the simplification step, it would work easily. So yeah, if you see a new compound like this, FeBr3, this 3 should go over here with the plus 3 state. There is nothing over here, which means it's 1. So the 1 over goes over here, minus 1. So that means Fe is equal to plus 3, Br is equal to minus 1. That's how that works. Makes sense?
Mhm. Yeah.
So either you have the reverse cross multiplication method, or you have the method of putting the values x and then finding that x based on the fact that sum of the oxidation states of all the elements in a compound is equal to 0, or that of an ion is equal to its charge. You can always find it. Once you find it, it's easy to correlate it with the left or the right hand side of the equation, pointing out which one is going with reduction, which one is going with oxidation. From there on onwards, it's easy, right?
Yeah. Yeah.
Good, good. So that actually finishes the whole chapter for us with along with the practice that we needed to go for this chapter. All right?
Yeah.
Good, good. Any questions?
No.